It still kind of blows my mind thinking about that 100-pound rotor blade just hanging up there.
Right.
How does something that heavy, well, how does it defy gravity like that? We actually got some amazing source material sent in from one of you, a whole chapter on helicopter aerodynamics.
Yeah, and diving into it has been really, really interesting.
Definitely an eye-opener. So let's unpack how these things actually manage to fly.
Exactly. This deep dive, it's really about tackling that core question. What are the fundamental forces that, well, let a helicopter fly? We've gone through this chapter, pulled out the key ideas, the surprising bits.
The goal being to give you a clear, kind of engaging picture without getting totally bogged down in like super technical jargon.
Precisely. Think of it as the highlight reel of helicopter flight principles.
Yeah, the express route. So we're going to focus on the big four forces, right? Lift, weight, thrust, and drag.
The fundamentals and the aerodynamic concepts behind them.
And the source even has some useful figures, diagrams showing the forces, the airfoil shape, the blade cross-section, even the blade area, which helps make it more tangible.
Yeah, figures like 2-3 for the forces, 2-2 for the airfoil, 2-1 for the area. They help visualize it.
And to help us navigate all this, we've got our expert here who's, well, brilliant at making complex stuff make sense.
Thanks. Look, what's really cool is how these four, seemingly simple forces interact. It's quite a dance.
So where do we start? Weight.
Let's start with weight. It's the most intuitive one. As the chapter says, it's simply gravity pulling down on the helicopter's mass.
That 100-pound blade example again.
Exactly. That's the force pulling it down. That's the challenge flight needs to overcome. Constant downward pull.
Right. So to counter that, to get the helicopter off the ground, we need lift. That upward push. Okay, how does that happen? What's the mechanism?
Okay, so lift comes from aerodynamic force. It's generated when air moves over an object, or, well, the object moves through the air. In this case, the rotor blade, the airfoil shape moving through the air.
That specific shape is key, isn't it? The airfoil.
Absolutely key. As air flows around that shape, it creates a pressure difference. Lower pressure above the blade, higher pressure below.
Ah, pressure difference. Now, the chapter mentions this huge static pressure at sea level, like 2,116 pounds per square foot.
Yeah, that's the atmospheric pressure pushing on everything equally from all sides. So normally it balances out, no net force.
But the airfoil disrupts that balance.
Exactly. It creates an imbalance. The trick is to make the pressure below the blade slightly higher than the pressure above it.
And even a small difference matters.
It really does. Across the whole surface area of the blade, even a tiny pressure difference adds up. The chapter notes like 1 pound per square foot difference on that 20 square foot blade from figure 2.1. That gives you 200 pounds of force. Oh, wait, no, the example was 100 pounds of force for that blade weight. Still significant.
Okay, so the pressure difference generates the lift. And this is where Bernoulli comes in. Faster air, lower pressure.
That's the principle, yes. Bernoulli's principle. It connects the speed of the airflow to its pressure.
Can you break that down a bit? Static versus dynamic pressure.
Sure. Think of total pressure as having two parts. Static pressure, which is just the air's sort of internal pressure, and dynamic pressure, which comes from the air's movement, its energy. Bernoulli found that in a flowing fluid like air, where the speed increases, the static pressure has to decrease, and vice versa, to keep the total energy, the total pressure, constant.
Like in that Venturio tube example, figures 2.5, 2.6, 2.7 show that constriction.
Exactly like the Venturi effect. The air speeds up in the narrow part, higher dynamic pressure, so the pressure drops right there.
So how does the curved top of the airfoil do the same thing?
Well, the air going over the curved upper surface has to travel a slightly longer path than the air going underneath in the same amount of time.
So it has to speed up.
It has to speed up, just like in the Venturi's narrow section. And that faster moving air on top means lower static pressure up there compared to the slightly slower air and higher static pressure underneath.
And that difference pushes the blade up.
That's lift. The higher pressure below pushes the airfoil toward the lower pressure above. It's mostly that pressure differential doing the work.
Makes sense. The chapter also says lift acts perpendicular to the airflow.
Right. The total aerodynamic force created by the airfoil can be split into two components. Lift, perpendicular to the relative wind, and drag, parallel to it, resisting motion. You want lots of lift, minimal drag.
And Newton's third law, action-reaction, the blade pushing air down.
Yes, that plays a part too. As the blade forces air downwards, the downwash, there's an equal and opposite upward reaction force on the blade.
Like a bird's wing.
Similar idea.
Yeah.
But for helicopters, especially in forward flight, the pressure difference from Bernoulli's principle is usually the dominant factor for lift. The downward deflection contributes, but often less so.
Okay, so lift isn't constant, right? What affects how much lift you get?
Good question. Several things, according to the source. Airspeed, faster flow, more lift. Air density, denser air, more lift.
Like flying lower versus higher up.
Exactly. Blade area, more surface, more lift. And critically, the angle of attack, or AOA.
Angle of attack, remind me, that's the angle between the blade and the oncoming air.
Precisely. The angle between the chord line of the airfoil, that imaginary line from front to back, and the direction of the relative wind.
And a bigger angle means more lift, usually.
Generally, yes, up to a point. For a symmetrical airfoil, you need a positive AOA, tilting the leading edge up to get lift. Zero AOA, zero lift.
But most helicopter blades aren't symmetrical, they're cambered.
Many are, yes. Non-symmetrical or cambered airfoils have that curved upper surface. Their advantage, they can actually produce lift even at zero or sometimes even a slightly negative angle of attack. Figure 2.4 shows this quite well. The shape itself helps direct air.
Clever. Okay, that's lift covered pretty well. Now thrust, that's the forward force, right? Or not just forward for a helicopter.
Exactly. Thrust is generated by the rotor system, yes, but unlike a plane where it's mostly forward, a helicopter's rotor thrust can be directed. Forward, backward, sideways, or even vertically, combined with lift.
So it's the force for movement and maneuvering.
You could say that. It's the force that overcomes drag, enabling movement in the desired direction.
Ah, drag. Always working against us. The chapter breaks it down. Profile, induced, parasite drag.
That's right. 3 main types. Profile drag is basically friction.
Just the blades moving through the air?
Yeah, 2 parts to it. Form drag, which is from the shape, the turbulent wake behind the blade. Figure 2.9 shows that turbulent wake idea. And skin friction, just from the air rubbing against the blade surface, even if it feels smooth.
Does profile drag change much with speed?
It increases, yeah, but sort of moderately with airspeed.
Okay. Then induced drag. That sounds more complicated.
It is a bit more complex. Induced drag is inherently linked to producing lift. Because you have higher pressure under the blade and lower pressure on top, air tries to spill around the blade tips from the bottom to the top.
Ah, creating swirls.
Exactly. Vortices, like little whirlpools trailing from the tips. Figure 210 gives a visual. These vortices mean the air flowing down through the rotor. The downwash or induced flow increases.
Okay. And how does that cause drag?
Well, remember, lift acts perpendicular to the relative wind. Because this induced flow points the relative wind slightly downwards, the lift vector also tilts slightly backwards.
Ah. So a component of lift is now pointing rearwards.
Precisely. That rearward component is induced drag. It's the price of lift, essentially.
And it changes the speed, too. But differently.
Yes. Interestingly, it has an inverse relationship with airspeed. It's highest at low speeds, like a hover, when you need a high angle of attack to get enough lift. As you speed up, angle of attack generally decreases, and so does induced drag.
Wow. Okay, so high induced drag when slow, high profile drag when fast. Ish. What's the third one? Parasite drag.
Parasite drag. This is the drag from everything except the lifting surfaces.
The fuselage, landing gear, rotor mast.
Anything that sticks out into the airflow and isn't designed primarily to produce lift. And this type of drag. It goes up drastically with speed.
How drastically?
With the square of the velocity. Double your speed, you get 4 times the parasite drag. At high speeds, it becomes the biggest drag component by far.
Okay, so you add all 3. A profile, induced, parasite to get total drag. And figure 211 shows that curve. There's a sweet spot.
Exactly. The total drag curve dips to a minimum at a certain airspeed. That point is where the lift-to-drag ratio is maximum LD max. It's the most efficient airspeed in terms of getting lift for the least amount of drag penalty.
Got it. All right, we've nailed the 4 forces. The chapter then really digs into the airfoil itself. It's more than just a wing shape, isn't it?
Definitely. An airfoil is engineered, designed to get much more lift than drag when it meets the air at the right angle. We use them for rotor blades, propellers, stabilizers.
And there's all that terminology. Figures 212 and 213 help here. Chord line, camber, leading edge, trailing edge.
Yeah, let's quickly define those. Leading edge is the front, trailing edge is the back. The chord line is a straight line connecting them.
And the chord is just the length of that line.
Correct. Now, camber refers to the curvature. The mean camber line is drawn halfway between the upper and lower surfaces. If it's curved, the airfoil is cambered, or non-symmetrical.
Which we said helps produce lift, even at 0 AOA.
Right. A symmetrical airfoil has no camber. Its upper and lower surfaces are mirror images. It needs that positive angle of attack to generate lift. Many helicopter blades are symmetrical, especially on lighter models, for certain handling characteristics. But cambered designs often offer better lift performance.
Okay. What about blade twist? Figure 214 shows the blade isn't uniform along its length. Why twist it?
Ah, blade twist. That's crucial. See, the tip of the blade travels much faster than the root near the hub.
Because it's covering a bigger circle in the same amount of time.
Exactly. So the relative wind speed is much higher at the tip. If the blade had the same angle all along, the tips would generate way too much lift compared to the root.
Creating huge stress near the hub.
Huge stresses and uneven lift distribution. So they build and twist. The blade angle, the angle of incidence, is higher at the root, slower air, and lower at the tip, faster air. This helps even out the lift production along the blade span.
Very clever. Okay, so blades are twisted airfoils, and their spinning creates what the chapter calls rotational relative wind. Figure 219 shows this.
Yes, just by spinning, the blade creates its own wind, flowing opposite to its direction of movement, mostly sideways across the blade.
And it's fastest at the tip, zero at the hub.
Correct. Now that's just from rotation. If the helicopter is also moving forward, as in figure 216, that forward speed adds another component to the wind the blade experiences.
And then there's the air being pushed down, induced flow or downwash. We mentioned that with induced drag, figures 217 and 218. How does that factor in?
Well, that downward flow of air changes the effective direction the wind hits the blade from. The rotational wind is horizontal-ish, but the induced flow adds a vertical component downwards.
So the actual wind hitting the blade is coming slightly from below the plane of rotation.
In a sense, yes, especially compared to the pure rotational wind. The more lift you generate, higher pitch, the stronger the downwash, and the more it alters the incoming airflow angle. It's most pronounced in a hover.
Which leads to the resultant relative wind in figure 220, the combination of rotation and downwash.
Precisely. That resultant relative wind is what the airfoil actually feels, and that's the wind direction we use to define the angle of attack. It's crucial for understanding lift and drag. Figure 221 shows how complex it gets when you add forward flight speed into the mix, too.
This brings us nicely to ground effect, IGE versus OGE. Figures 222 and 223 show different airflow near the ground. Why is hovering near the ground easier?
Ah, ground effect. When you're hovering close to the surface, say, within one rotor diameter, the ground physically restricts that downward induced flow.
It can't flow down as freely.
Right, it sort of cushions the air. This reduces the downward velocity of the induced flow. Less downwash means the resultant relative wind becomes more horizontal.
And a more horizontal wind increases the angle of attack for the same blade pitch.
Exactly. For the same collective pitch setting, you get a higher effective AOA, which means more lift. Plus, those tip vortices we talked about, the ones causing induced drag, they can't form as strongly near the ground.
So less induced drag, too.
Correct. More lift, less induced drag, means you need less engine power to hover in ground effect, IGE.
And out of ground effect, OGE, when you climb higher,
You lose those benefits. The induced flow increases, becomes more vertical. That reduces the AOA for a given pitch setting.
so the pilot has to pull more collective, increase the pitch.
Yes, which demands more power from the engine just to maintain the hover. The chapter even mentions the danger of vortex ring state, which is related to descending too quickly into your own downwash.
Okay, understanding the airflow is key. Now, let's clarify those blade angles again. Angle of incidence versus angle of attack. Figures 224 and 225.
Good distinction to make. Angle of incidence, or pitch angle, is the mechanical angle. It's the angle between the blade's chord line and the rotor hub plane.
The angle the pilot sets with the controls.
Exactly. The pilot uses the collective lever to change the pitch of all blades together and the cyclic stick to change the pitch of blades individually as they go around the rotor disc.
An angle of attack.
That's the aerodynamic angle. It's the angle between the chord line and that resultant relative wind we just discussed.
The blade actually experiences, influenced by downwash, forward speed, etc.
Precisely. So the pilot controls incidence, but it's the angle of attack that directly determines how much lift and drag the blade produces at any moment.
And more AOA means more lift, but only up to the stall point.
Correct. Increase AOA, lift increases until you reach the critical angle of attack. Go beyond that, the airflow separates from the top surface, lift drops dramatically, that's a stall. So the pilot manages AOA indirectly via the pitch controls. Blade flapping, which we'll get to, also affects AOA automatically.
Okay, let's move into powered flight. Hovering seems like it should be simple, just balance lift and weight, right? Figure 226 shows the forces. But the chapter says it's really demanding.
It looks simple, but yeah, hovering is tough. The helicopter is sitting in its own messy, turbulent downwash. It's constantly trying to drift or change altitude or heading.
So the pilot is always making tiny corrections.
Constantly. Tiny cyclic inputs to stop drift, tiny collective adjustments for altitude, throttle tweaks, or the governor does for RPM, and pedal inputs for heading. It's a continuous balancing act. Lift equals weight. Thrust from a slight rotor tilt and tail rotor equals drag and tail rotor side force.
And adjusting the collective directly controls that lift component for going up or down.
Exactly. Pull up on the collective, pitch angle increases, AOA increases, lift increases, you go up. Lower the collective, the opposite happens.
What about drag in a hover? Is it mostly that induced drag we talked about?
Primarily induced drag, yes, because you're generating a lot of lift at zero or very low airspeed. There's still some profile drag from the blade spinning and a tiny bit of parasite drag.
And torque. Figure 227. The main rotor spins one way, the body wants to spin the other. Newton again.
Classic Newton's third law. Engine turns the rotor. Rotor tries to turn the fuselage the opposite way via torque. The tail rotor's job is to produce sideways thrust to counteract that torque.
Keeping the nose straight.
Or allowing the pilot to yaw the helicopter using the pedals, which control the tail rotor pitch. More engine power means more torque, so you need more tail rotor thrust.
Then there's translating tendency, that sideways drift.
Yeah, for single main rotor helicopters, the tail rotor thrust pushing sideways also pushes the whole helicopter slightly sideways.
So it doesn't just hover perfectly still.
Not without compensation. Engineers design ways to counteract it and maybe tilt the transmission slightly or rig the controls with an offset or design the fuselage to hang slightly tilted. In forward flight, it shows up as a slight inherent side slip needed to fly straight.
Figure 228 shows pendular action, the helicopter swinging under the rotor.
Right. The heavy fuselage hangs below the rotor hub like a pendulum. If the pilot makes sharp, jerky control inputs, they can set up this swinging motion. Smooth, deliberate controls are key for stability.
And coning. Figure 229, the blades flex upwards.
Yep. When the blades are producing lift, upward force, and spinning, creating outward centrifugal force, they naturally find equilibrium by flexing upwards into a shallow cone shape.
Is that bad?
A certain amount is normal, but the amount of coning depends on lift and RPM. If RPM gets too low, centrifugal force weakens, the blades cone upwards excessively, and that's very dangerous. They could hit the tail boom or even each other.
Okay, low RPM is bad. Now, Coriolis effect and gyroscopic precession, figures 230, 231, physics time.
Hey, yeah. Coriolis effect, conservation of angular momentum. Think of the ice skater pulling their arms in to spin faster.
How does that apply here?
If the blades cone upwards, their center of mass moves slightly closer to the axis of rotation. Theoretically, this could cause the rotor RPM to speed up slightly, though governors usually handle this.
And gyroscopic precession sounds complex.
It's a property of any spinning object, like a gyroscope or a rotor disc. If you apply a force to change its angle, the effect doesn't happen where you applied the force, but about 90 degrees later in the direction of rotation.
So if the pilot wants to tilt the rotor disc forward, they don't apply the force at the back.
Exactly. The control system is designed so that when the pilot pushes the cyclic stick forward, the maximum blade pitch change happens when the blade is off to the side, causing the disc to tilt forward 90 degrees later. Pilots have to anticipate this lag.
Mind-bending. Okay, let's move away from hovering. Vertical flight. Figure 232.
Pretty straightforward, aerodynamically. More collective pitch, lift exceeds weight, you climb vertically. Less collective, weight exceeds lift, you descend. In a steady climb or descent, forces are balanced again, just with vertical motion.
And forward flight, figure 233, tilting the whole disc forward.
That's the key. Pilot uses forward cyclic. The tip path plane tilts forward. The total rotor thrust vector now points forward and up.
Splitting into two components.
Right. A vertical component still counters weight, lift, and a horizontal component becomes thrust, pulling the helicopter forward against drag. Figure 234 shows how power needed changes with airspeed that dip near LD max again.
But forward flight messes with the airflow across the disc, right? Figure 235 shows that. Leads to dissymmetry of lift. Figure 236.
Yes, this is a major factor. The blade moving forward, the advancing blade experiences higher relative wind speed, its rotational speed plus the helicopter's forward speed.
So it generates more lift.
Much more. Meanwhile, the blade moving backward, the retreating blade experiences lower relative wind speed, rotational speed minus forward speed, so it generates less lift.
That sounds like it would want to make the helicopter roll over.
It would, except for blade flapping. Fact 237 illustrates this. Most rotor systems allow the blades to flap up and down on hinges, or flex.
How does that help?
As the advancing blade generates more lift, it naturally flaps upwards. This upward movement decreases its effective angle of attack, automatically reducing its lift.
And the retreating blade?
It generates less lift, so it flaps downwards. That increases its angle of attack, increasing its lift.
So flapping automatically compensates?
It's the primary compensation method, yeah. Along with cyclic feathering, where the pilot, or flight control system, makes small pitch adjustments to the blades as they rotate, but there's a limit.
Retreating blade stall.
Exactly. At high forward speeds, the relative wind over the retreating blade can become so slow and its required angle of attack so high that it stalls. This causes vibrations and a tendency to roll, and it sets the helicopter's maximum speed limit, the VNE.
Wow. The chapter also mentions blowback, figure 238, nose pitching up.
Yeah, that's a tendency during acceleration into forward flight. As flapping increases to balance lift, the whole rotor disc can tilt back slightly, causing the nose to pitch up. The pilot just corrects with a bit of forward cyclic.
Okay. Then figures 239, 40, 41 talk about translational lift and ETL. That sounds positive.
Very positive. As the helicopter gains forward speed, the rotor starts moving into cleaner, undisturbed air instead of recirculating its own downwash like in a hover.
Getting away from its own turbulence.
Exactly. This improves the rotor's efficiency significantly. You need less power for the same lift. That's translational lift.
And ETL, effective translational lift.
That's when the effect really kicks in strongly, usually around 16 to 24 knots. The rotor is fully clear of the recirculating downwash. The airflow becomes much more horizontal, induced drag drops. You often feel a shudder or vibration as you pass through ETL, and the helicopter wants to climb or accelerate. Big efficiency gain. The source also mentions transverse flow effect, a vibration around 10-20 knots from airflow differences front to back across the disk.
Okay, efficiency boost with forward speed. What about sideward flight? Figures 242, 43, just tilt the disc sideways?
Pretty much. Use the lateral cyclic to tilt the disc, generating sideways thrust. But the chapter warns it can be less stable.
Why?
The fuselage presents a lot more drag sideways, and there's no vertical fin or horizontal stabilizer optimized for that direction, so it requires more pilot attention, smoother inputs, and you have to be very aware of the disc's proximity to the ground to avoid dynamic rollover.
And rearward flight? Figure 244, tilting the disc back. Also hazardous?
It has its own risks. Tilt the disc back with aft cyclic, but the horizontal stabilizer, if you have one, can catch the air flowing backward and push the tail down.
Potentially hitting the ground.
Especially if moving backwards into wind, yeah. Plus, landing skids aren't really designed for easy rearward sliding, so caution, clear the area, smooth inputs are key.
All right, nearly there. Turning flight, figure 245. Banking the helicopter.
Just like an airplane, really. Use cyclic to roll into a bank. The tilted lift vector now has two jobs.
Vertical part for weight, horizontal part for the turn.
Exactly. The horizontal component provides the centripetal force, pulling the helicopter around the turn. The steeper the bank, the more lift is directed sideways, the tighter the turn.
But less lift is available vertically.
Correct. So to maintain altitude in a turn, especially a steep one, the pilot needs to increase total lift by pulling up on the collective, increasing the overall blade pitch and AOA.
Makes sense. Finally, autorotation, figure 246. The big one, engine failure.
The critical emergency procedure. If the engine quits, a freewheeling unit automatically disconnects it from the rotor.
So the rotor can spin freely?
Yes. As the helicopter descends, the air flows upwards through the rotor disc. This upward airflow actually drives the blades around like a windmill.
Keeping the rotor spinning to provide some lift.
Exactly. It won't stop you falling, but it controls the descent. Figures 247 and 48 show the blade regions in a vertical autorotation. A driven region near the tip, a driving region in the middle that keeps it spinning, and a stalled region near the root.
And the pilot uses collective pitch to control the rotor RPM.
Yes, manages RPM and descent rate. Figure 249 shows how it looks in forward flight autorotation. The goal is to manage the descent and then, just before landing, use the stored rotational energy in the blades for a flare, a quick increase in pitch to cushion the touchdown.
Incredible that it's even possible. Phew, okay.
Yeah.
That was quite the journey through helicopter aerodynamics. From the basic forces to some really complex interactions.
It really covers the gamut, doesn't it? It's amazing how all those principles, lift, weight, thrust, drag, airfoil shape, AOA, rotor dynamics, have to work together perfectly.
It gives you a whole new appreciation for what's happening just to get off the ground and maneuver.
Absolutely. Understanding these fundamentals, even at this level, really highlights the engineering and the physics involved. It's not just brute force. It's elegant manipulation of airflow.
Totally. And hopefully, for you listening, this deep dive has shed some light on that initial question, how does that heavy machine stay up there? It's answered some questions, maybe sparked some aha moments.
We hope so.
Yeah.
It shows that even something seemingly straightforward involves this incredibly complex interplay of forces and design.
It really does. You know, it makes you think. These same fundamental forces, lift, drag, thrust, weight, they govern so much more than just helicopters. How do they play out elsewhere in aviation or even in nature? Something maybe to ponder on your own. It's all connected in fascinating ways.